The rest of the lecture is dedicated to the anti-de Sitter spacetime, which is a solution of the Einstein equations with the minus sign, d minus 1. I remind you that it solves this equation, d minus 1 times d minus 2 over 2h squared g mu nu. Well, this is a metric tensor, this is an Einstein tensor. So it solves with the minus sign, so it's a space with constant negative curvature. And it can be obtained also geometrically as the following hypersurface, hyperboloid actually also, embedded in a bit different space-time. So like it is defined like this, d minus 1 h xj squared minus xd squared equal to minus 1 over h squared. Compared to the de Sitter space, there, if we take this to minus, to this side, this will be with plus sign. All of this will be with minus sign, and this will be again with the plus sign. We have a bit different signature here. We have two minuses and extra pluses, while in the de Sitter space we had one minus and the rest was plus. So this hyperboloid is embedded into the following very strange space-time with the following metric. Unusual so far, we never encountered it. d minus 1 dx j squared plus dx d squared. So it has a signature plus, minus, 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 so forth. Minus, and then the final plus. So it has two pluses, so to say 2 times, and the rest as spatial coordinates. So let's see what happens with this space under Wick rotation. So let's change xd here and here, xd to ixd. What happens? Then we get here plus sign and here minus sign. So what is this? Then this is a regular Minkowskian space. And what is this? This is actually the following space. So after this, we obtain the following actually hyperboloid. J from 1 to d xj squared. Now it runs from 1 to d, while here it was to d minus 1, but with extra plus here after this rotation we obtain this, and this is equal to 1x squared. So what is this? What do we have? As a result, we have that sum over j x j squared equal to x0 squared minus 1 over h squared. We have already encountered such a space in the previous lectures. This for the case when it was three-dimensional or four-dimensional. Oh no, three-dimensional, when d was actually ranging to 4 here, then to 3, sorry, to 3 here. In fact, this is a two-sheeted hyperboloid because it has one sheet for x0 starting with h, 1 over h, and the other sheet starting with h x0 less than 1 minus 1 over h. We encountered it for the case when h was equal to 1. So this is a Lobachevsky space, d plus 1 dimensional. So we have embedded into d plus 1 dimensional Minkowski space, we have embedded d-dimensional Lobachevsky space. D-dimensional Lobachevsky space. And Lobachevsky space is known to have a constant negative curvature. And that's the reason this space-time, which is called anti-de Sitter space-time, has a constant negative curvature. So while de Sitter space was mapped under Wick rotation to the sphere, under Wick rotation, in this case, we obtain hyperboloid. So actually, under this kind of maps, this or similar for different coordinates, and map of H to IH. We can define maps between d-dimensional sphere, d-dimensional Lobachevsky space, d-dimensional de Sitter space, and d-dimensional anti-de Sitter space. All of them can be mapped by various variations of this relation. Note that this map changes the sign of curvature. So under this map we get plus here instead of minus. So all of these maps allow us to map all these spaces to each other, and actually under this map all the embedding spaces are mapped to each other, and also the equations are mapped to each other. So these kind of maps allow us to understand the geometry of all these spaces in a unique manner. So we can understand geodesics, as we did that for the sphere and for the de Sitter space. We can understand also the hyperbolic distance in anti-de Sitter space, etc., etc. So this is a simple method to understand the geometry and physics in these spaces. Although these kind of maps do not go too far. The geometry is mapped, but some of the physics, not always, is mapped on this space. Well, just to list one complication which happens, which goes beyond the discussion of our lectures, is that, for example, if one considers green functions in these spaces, they are not mapped under these maps. Well, some of them do, but not all of them. If you just naively apply this map for the green function, you obtain wrongly behaving green functions in some cases.